Thank you for joining the hands-on workshop, Performance Optimization for Intel Xeon Phi Processors. This is episode 7. I'm Andrei Vladimirov with Colfax International. In this episode, I will demonstrate vectorization with AVX 512. If something doesn't sound familiar, you can revisit session number 3. And this is where I talked about vector instruction support in Intel Xeon Phi processors. I have a specific workload with which I want to illustrate vectorization. This workload performs binning. Binning, of course, is an operation that you commonly find in statistical workloads and in Monte Carlo simulations. I have an artificial example that is relatively easy to understand, and we will see how new features in Knight's Landing help this code to vectorize. Suppose I have an array that contains ages of multiple people, and this is a long array. Think of millions of entries. Every age is a floating point number from 0 to 100, and my goal is to compute how many people I have in the age group from 0 to 20 years, how many people in the age group 20 to 40, how many people in the age group 40 to 60, and so on, 60 to 80, and 80 to 100. I'm assuming that no age is greater than 100. In serial code, this is of course trivial to do. I take the age of one person divided by the group width, which in my case is 20 years, and this gives me a number that I need to round down to the nearest integer. And this integer I will use to compute the location of the counter that I need to increment. So this is basically the group number. Clearly, there is opportunity for data parallelism in this code. If I can take one age and divide it by the group width to get this intermediate number, clearly I can do it for several ages at the same time by loading them into vector lanes and dividing this vector by a vector in which every lane is equal to 20, the group width. The next operation, converting the floating point number to an integer, is also vectorizable. I can take a vector of these numbers, call a vector instruction that converts it to a vector of integers, and this will give me the vector of group numbers. But this last step, where I use the group number to go to a certain location in memory and increment the counter there, that one is tricky. Because if in one vector lane I have the value 2, I go to age group number 2, but in the next lane I may have the same exact value. And that's a problem, because I have a conflict. In fact, on older Xeon processors and on third generation Xeon Phi, this loop will not vectorize at all. But on Knight's Landing, second generation Xeon Phi, thanks to AVX 512 conflict detection instructions, this loop is going to get vectorized, and we will see what it takes to make this happen. I will illustrate this process hands-on on a workstation that has an Intel Xeon Phi processor in it. So this is my server. This is one of the machines from dap.xeonphi.com. It has Intel Xeon Phi 7210 CPU with 64 cores clocked at 1.3 GHz. I already have the file that contains my code, the same exact code as I showed in the slides. Let's compile this code and see what happens. Intel C++ compiler, please compile worker.cc, and as you compile, please produce an optimization report with the highest verbosity. So this is what this command is doing. Alright, so I compiled, and let's see what's inside of this file. This is a text file, and for the function histogram, it has a remark about the only loop found in this function. And the remark is that the loop was not vectorized, because vector dependence prevents vectorization. And vector dependence is spelled out here. It is in line 29 between the hist that you are incrementing and the hist into which I am writing out. But basically, what I want to point out is this: loop was not vectorized. Well, this is not satisfactory, and we need to come back and see how we compile the code. We compile the code in such a way that the compiler will produce a conservative executable. In fact, we can change this, and we can request that the compiler makes an executable tuned for second generation UNFI. Starting from compiler version 15, you can do that, and all you have to do is specify -xmic AVX 512. If this slide looks new, then please revisit episode number 3. Okay, let's test this in action. I will call the same command, but I will add to it -xmic AVX 512, and I will reread the vectorization report. Now, in the vectorization report, I have very different information. There is information about loop peeling and its vectorization, and down the line here's the main code of the function. Loop beginning in line 23 was vectorized, and that's good news. It is vectorized, and the compiler treated the hist array gracefully by generating a scatter and a gather for it. It makes a comment about divides in the loop, which is something that I can address before I move on, and this is something easy to understand. The division operation is usually a lot slower than multiplication. It does apply to nice linear architecture, and let me show you what happens when I replace division with multiplication, and then I will follow up with performance results. I will define a new floating point number, 1 over group width as 1 divided by the group width. And instead of dividing by the group width in every loop iteration, I will multiply by 1 over group width. Let's recompile the code. And now, in the optimization report, there are no comments about division, and still the loop was vectorized. We can see what exactly the compiler did to the code if we replace -c with -s. This produces assembly listing, and it goes into file worker.s. It is curious studying this assembly. So this is the assembly. As I go down, I will eventually find the beginning of my loop. And here it is. Here is a vector instruction that multiplies the previously loaded value of ages by the previously created vector with the reciprocal group width. This is an operation on packed single precision numbers. Then it converts the vector of packed double precision numbers into a vector of signed integers. And here is the crucial operation, conflict detection. So this is the operation that allows this entire loop to vectorize. If we were compiling on a processor, for a processor that doesn't have conflict detection instructions, we would still be able to vectorize this loop partially. And I have code to show you that illustrates how this would be done. We would have to take the loop and strip mine it. Basically express it as two nested loops. One iterating with a stride of 16, and the other operating with a stride of 1, but with only 16 iterations. In this loop, we would do the multiplication and the conversion to integers. And there will be another loop which cannot get vectorized, and in this loop we would do the histogram increments. So it is still possible to vectorize binning if you don't have conflict detection, but it requires more programming effort. I have a slide that summarizes performance, and there's something interesting to learn from this slide. What I'm showing here is the performance of this code measured in billion values binned per second, so higher is better. I measure performance on 3 systems: a general purpose Xeon, first generation Xeon Phi, and second generation Xeon Phi. This is what I had in my server. Of course, there's a huge gap between the CPU and the Xeon Phi, and this gap is because we have serial code. If you wish to continue listening to this presentation, you will see how the performance that we had in the previous slide is going to get translated into parallel performance through OpenMP. So we have a single threaded code that we want to parallelize across threads. I will show you how we are going to do this, but first let's establish the baseline. I'm going to run the code as we have it. It is going to be compiled with Mike AVX 512, so it's vectorized, and we see 1.2 times 10 to 8 values binned per second. This code is only using one thread, and if you want to add multi-threading, we need to look at loops. There's just one loop in this application, so I'm going to try to parallelize it across threads with OpenMP. If I try to do that, it will lead to a problem. Different threads are going to increment the histogram at the same time. This will lead to a data race and incorrect, unpredictable results. I can try to change this by protecting this data race with a mutex. For example, pragma OMP atomic will guarantee that even though multiple threads are writing here, the result is going to be correct. If I try to run this code, I will see that the performance actually degrades by a large factor. This is what we had in the serial code, and if we wait long enough, we will find that the parallel code actually gives me 1/10 of that performance. So this is not a good way to do that. Instead, I will use a parallel pattern that is called reduction with thread private variables. To do that, I will split pragma OMP parallel into 2 pragmas, pragma OMP parallel and pragma OMP4. This will give me the opportunity to insert some code before the parallel loop, and I will declare a thread private container. Each thread will have one. It will be initialized, and where I have the data race, I will avoid the data race by using the thread private container to accumulate a partial result. Finally, at the end, I will have to reduce, meaning aggregate all thread private containers from all of the threads to the shared container, and I will do it like this. I will have to use a mutex here because we are still in a parallel region, but this is going to be economical because I will issue very few mutexes compared to the original code. When I run this code, I see that my performance jumps up and I achieve 1.4 times 10 to 10 values per second. Compare this to our original single-threaded performance, which was 100 times lower. I could stop here, but I know that there are some additional opportunities for tuning, particularly the high bandwidth memory. All I have to do to run this application in high bandwidth memory is numactl m1, and of course I could use libnuma instead, and we discussed this in session 6. The first run seems to have been a fluctuation, but a more consistent result is what I obtained on the second run, and if I keep running, it gives me around 2 times 10 to 10 values per second. So this procedure allows me to improve performance on my Knights Landing processor very significantly, from 0.2 to 20 billion values per second. The same procedure actually also worked for a Xeon, and it worked for a Xeon Phi coprocessor. You can see that their performance also was improved by a large factor. And how did I do this so quickly, and how did I know what to do? We discussed this in the How series, and you can refer to session number 7. This is where we do this exercise in greater detail. I could stop here, but I want to be honest and continue optimization, because I optimized memory access on Xeon Phi. How about optimizing memory access on Xeon? And indeed, there is room for optimization through parallel first touch. I can do something to the code that, instead of producing what I just saw, the Xeon almost doubles its performance. And this is done through parallel first touch. If you want to learn more, attend the How series, session number 8. You can see that this optimization technique did not change the performance on Xeon Phi. And at this point, you see that the CPU is actually faster by 10% than my Xeon Phi. Is that a problem? Let's think about that. In my calculation, I have the age multiplied by the reciprocal of the group width, and this is all converted into an integer. So I have 2 vector instructions, and after doing these 2 vector instructions, I will be incrementing my histogram. And I will do it 16 times. This is how many values I have in a single vector instruction. Clearly, this workload is mostly scalar. And even for a scalar workload, Xeon Phi of the second generation is almost on par with a powerful Xeon. If this is the type of workload that you are running, Of course, you can go by these numbers, but you need to realize that there are several metrics of performance that could be important. What I'm showing here is the performance per system, per physical system. But some other important metrics could be performance per watt if you're running a data center, because if you look at the specifications, the thermal design power of the CPU is around 300 watts, whereas the thermal design power of the Xeon 5 processor is around 215 watts. So I do 10% less work for 30% less power. Another metric of performance that could be important is performance to cost ratio, and I'm not in the position to provide up-to-date information about costs in a recorded video, but this is something that you can definitely research on your own. This concludes episode 7, and in the next episode, number 8, I will talk about the Intel Math Kernel library and about tuning your application performance with calls to the Intel Math Kernel library and also tuning the environment in which it runs. See you there!